Assalamu alaikum. I'm your teacher Muhammad Ikram from Pakistan International School, Taif. From Pakistan International School, Taif. Today is lecture number 6, Unit Electrostatic, and one of the most important topic that is Gauss law. So let us start with the name of Allah Almighty. Bismillah Rahman Rahim. Now, what is Gauss law? Gauss law is one of the most important law, and once when I write the statement, I will explain to you the concept of the Gauss law, that where the Gauss law is applicable. According to the Gauss law, this law states that this law states that the electric flux through the electric flux through a closed surface is always equal to 1 over epsilon naught times the charge enclosed by the surface. The charge enclosed by the surface, or we can say that the electric flux through a closed surface is 1 over epsilon naught times the charge enclosed by the surface. The charge enclosed by that surface, or the charge enclosed by the surface. Mathematically, we can write that the electric flux pi through a closed surface is equal to 1 over epsilon naught times the charge enclosed by that surface, right? Or we can write that E dot A equals that E enclosed by epsilon naught. This is the mathematical form of the Gauss law. Now, Gauss was a French mathematician and physicist, and he introduced one of the most important law, which is able to solve different complex phenomena when solved through the Coulomb's law. If you remember, I told you that the Coulomb law is very difficult to applicable to certain situation. And what were those certain situation? Those certain situation was that what happens that when the charges are more than 3, for the 4, for the 3, it was very easy to apply the Coulomb's law. But when there is charge distribution, for example, as I told you that when we have what? If you remember, I told you that we have charge distribution. Charge distribution means if the charge is distributed all along the body, and one we have the isolated system of charges like system of charges from like Q1, Q2, maximum up to Q3. To this system, this can be easily solved by what? Easily solved by Coulomb's law. By Coulomb's law. But difficult for this, difficult, difficult, difficult. And for this, it is easy. So this is why we will look towards certain points where we can help, where we, the kind of laws which can help us to calculate the electric flux, the electric field intensity due to any charge distribution. So I just want to tell you first about the concept of the Gauss law, and then I will revisit this once again, that what is in fact the concept of the Gauss law. The concept of the Gauss law is, that is, what is its concept? The concept of the Gauss law. The concept of the Gauss law is that number one, the concept of the Gauss law is, that is, we can calculate the electric field intensity. We can what? That we can calculate, we can calculate the electric field intensity. The electric field intensity, the electric field intensity if the charge distribution is known. If the charge distribution, if the charge distribution is known. This is one of the most important point. If the charge distribution is known, then we can calculate the electric field intensity at any point. Second important concept is that the electric flux, the electric flux through any closed surface, through any closed surface, depends upon what? Depends upon number A, this one. As you see, it depends upon this one. What is that? This one, charge distribution. Charge distribution. Yeah, the charge enclosed by that surface. Charge enclosed. And second, it depends on what? The second thing on which it depends is number B. And what is that B point? That is the nature of the medium. Nature of the medium. It depends on what? The nature of the medium. That is what? Dielectric constant. Depends on what? Dielectric constant. That what is the kind of medium? That is second one. The third important point here is, which you will notice, is the one that number C, charge distribution, that is electric flux through any closed surface. Electric flux does not depend on the geometric shape of the body, on the geometric shape of the body, yeah, of the closed surface, right? So these are the few important points, and then I will show you them one by one. So what is the most significant part of the Gauss law? The most significant part of the Gauss law is that we can find the electric field intensity. That we can what? That we can find the electric field intensity. We can find the electric field intensity if the charge distribution is known, one, right? Or we can calculate the charge distribution the amount of charge on a surface if the electric field intensity is known. So this is only applicable. Another important point is that it is only applicable to symmetric charge distribution. Symmetric charge distribution. And another one, there is the importance of that closed surface, right? The surface must be closed. Sometimes we call it the Gaussian surface. The Gaussian surface must be constructed, must be constructed, must be constructed around any charge distribution. This is important, and later on we will do it in the application of the Gauss law. Another sorry, another important point is that what is actually this charge enclosed. The charge, sometime I write E and C, in your book it will be just only capital Q. That is charge distribution. And this charge distribution can be found by using surface charge density. This can be found by what? By charge density. This surface charge density, it could be a line charge density, surface charge density, bulk or volume charge density. So this is charge per unit length, right? This is usually denoted by lambda, and this is charged enclosed per unit length. This is surface charge density by sigma, charge enclosed per unit area. So if the surface charge density is known, then we can write it as what? That we can write this, that the charge enclosed will be equal to A into surface charge density. And this volume charge density, that is charge per unit volume, charge enclosed per unit volume, may be denoted by beta or whatsoever, I don't remember. So sorry for that. So that is the charge density. This is what we must know first in order to solve. About this, I already told you, right? Then we can calculate the electric field intensity. This is what the net or the total electric flux. This one is what? The net electric flux. Net or total flux. The total flux through any closed surface. There is no derivation for the Gauss law. Laws are discovered or investigated. They are not derived. So if it is there in your book, so I think it is not reasonable. However, we can just explain it from certain examples. For example, let us see, look at this diagram. See here, and let me drop it here. Paste. Good. You see, look, there the Gauss law is applicable to both kind of surfaces. Regular shaped surfaces, for what? For regular. The surface must be regular shaped surface, like that one, or irregular shaped. Irregular shaped, it doesn't matter, right? For example, look this one. Right now, let us see that how we can apply the Gauss law to this surface. In order to calculate the electric flux through this sphere, enclosing a charge Q at the center. This is what? This is a charge Q that is at the center of the sphere. A charge Q is enclosed at the center of the sphere. So electric flux through the surface of at the surface of this what of this sphere due to a charge enclosed, right? So first of all, for example, if you have a charge enclosed, then at the sphere, so this is actually our what, this is our Gaussian surface, right? Now what is the formula for the electric flux? The formula for the electric flux is what? That is the Gauss law. We now derive the Gauss law from this. What is the formula for the electric flux? The formula for the electric flux is E dot A, right? Now you see that, look, since if you just look around this charge particle, you just see there is a charge, and you see that, look, what we are actually going, since this is a sphere, so we will divide this sphere into what, into many length element, right? And we will calculate the electric flux through each of the length element, like this one. These are what, the various surfaces, right? You label it a small surface delta A1, then this will be delta A2, this will be delta A3, this will be delta A4, up to this one will be delta an minus 1, and this will be delta an, right? And similarly for everyone there will be what, the area vector. As you see, this is what, this is the area vector, area vector, right, in the direction of the length element delta A1. Now you see that from every charge particle, that is from every length element, this is the electric field intensity E at this point. This is the electric field intensity E at this point. This is also the electric field intensity through this. This is also the electric field intensity. And this is also the electric field intensity through this point. So look, and here we have the length element. The length element for this is delta, for delta A1, sorry, delta an minus 1. Here it has the area vector n minus 1, and like here that you have the area vector a delta a2, like that, okay? And similarly you have what, you have the electric field intensity at this point. So let us calculate the electric field intensity to each and every element. As we know that, is we know that what is electric flux through the surface 1, it will be E1 dot delta A1, or it will be equals E1 delta A1 cos theta 1, right? That is what, that is the theta is the angle between what, for example, you see, look, there might be the angle between what, this is the angle between theta, angle between what, between E and A for every length element E and delta A, right? So here this is theta, for example, you will be having here theta 1, there you will be having, this is E, and this, if I just mark this, is this one, look, you have here delta A2, A4, so you have the theta here, theta 4, like that one. So similarly, you see, look, for every length element, I'll be writing 2 E2 dot delta A2 or E2 delta A1 into cos theta 1. Similarly, for E3, E2 delta A3 into E3 into delta A3 into cos theta 3. Similarly, pi n minus 1, this will be equal like this one and this one, this whole, it will be equal to E n minus 1 into delta A n minus 1 or E n minus 1 delta an minus 1 into cos theta 3n, n minus 1, or the last one, en will be equal en into delta an minus 1 equals en delta an into cos theta n. Now there are some important points here which I want to look now. As we know that E1 will be equal E2 will be equal E3 will be equal En minus 1 will be equal En will be equal E. Why? Because what is the reason? Because we know that what is the electric field intensity for a point charge. The electric field intensity for a point charge is equal 1 over 4 pi epsilon naught into this q by r square. Since for every length element, for every area element delta A, R is the same. R is what? R is the same. So E the same. E is what? E is the same. So E is constant. What does this means? This means that this means that this means that E is what? This means that E is constant at the surface. It is what? At the surface of the closed object. E is all constant. So now adding another important point, that is E1. Similarly, theta 1 is equal to theta 2 is equal to theta 3 is equal to theta n minus 1 is equal to theta n is equal to 0. Right? Why? Because that is delta A and E are the same, are in the same direction, are in the same direction for every length element, for every length element. It is the same for what? For the every element, for every length element. Okay. So putting all these values, right? This thing. So similarly, therefore, cos theta everywhere will be cos of 0, which will be equal to 1. So going back to our equation number 1, this equation, right? Now look, the total electric flux, the E, the total electric flux through the closed surface will be equal to psi 1 plus psi 2, pi 1, pi 2, pi 3. I'm sorry, class, sometime I call it a psi. This is just my kind of habit. I'm sorry for that. It is pi. So this will be equal to plus n minus 1, and this will be equal to plus n. So we have won this. So the electric flux will be equal, this electric flux, total electric flux through the closed surface will be equal to what? It will be equal to E delta A1 plus E delta A2 plus E delta n minus 1 plus E delta A n. Why? Because E1, E2, E3 all the same. Cos theta is equal to what? Cos theta is for the zero angle. Cos theta is equal to always 1. So I just wrote this thing. Now you know this is E dot what? This will be equal. This is electric flux, right? This electric flux will be equal what? It will be equal to E, and this will be equal to what? Delta what? This will be equal to delta, it will be equal to what? This will be equal to delta A1 plus delta A2 up to delta n, right? So you see, if you have a sphere like this, and if you just like a football pitches, a1, a2, a3, right? So if you all add them together, these small areas, it will be the area of a sphere. So this is nothing but what? Area of the sphere surface. This is area, and this area is always equal to 4 pi r square. It is equal to this thing. So what does this implies? That this E is equal to E into 4 pi r square. But for a point charge, for a single charge or for a point charge, we know that the electric field intensity E equals 1 over 4 pi epsilon naught into q r square, right? So what does this means? This means that this psi is equal to what? That is equal to 1 over 4 pi epsilon naught q r square into 4 pi r square. So this r square gone, this pi and pi gone. So what is left? That psi is equal to what? This q into epsilon naught. But remember, that was a single charge, but this could be a charge distribution, charged enclosed, we call it, right? So the electric field intensity due to a point charge enclosed by a surface is equal to k q by epsilon naught. Now you see this equation tells you that, look, that it does not depends on what? That electric flux does not depends on the geometric shape. Electric flux what? Electric flux does not depends on what? Depends on the geometry, yani the shape of the closed path, closed surface, right? Now why? Because that is, you see here, I'm thinking this is very, very important, remember, right? Why? Because you know what is electric flux? E into A. Very simple answer, simple answer to this, not stories. You see, look, what is this? If you see, look at this thing here. What is this? This is electric field intensity, 1 over 4 pi epsilon naught r square cube. And this is A. A could be pi r square, 4 pi r square, or whatsoever for any surface. Here you see E is inversely proportional to r square, but here you say A is directly proportional to r square. So if you increase the radius, E automatically decreases, or if you decrease r, A automatically decreases, and so that you have this thing the same, electric flux the same. This is why electric flux does not depends on the shape and geometry of the closed path, and it will be always EA, or in term of Gauss law, it only depends on the charge enclosed, that how much is the charge enclosed, and it depends on the medium. So this is one of the most important result. Here you see this is for the regular shaped object. Look at the irregular shaped object, that what will happen for the irregular shaped object. You just see, look, let us do it for that irregular shaped object, that how we can apply this thing, how it does not depends on the geometry. You just see, look, as you see, look, this is what? This is a kind of irregular shaped object. For this irregular shaped object, if you apply, look, the Gauss law to this one, so you see, look, what you will do. You have the charge distribution, various charge distribution. Here is Q1, here is Q2, here is Q3, this is Q4, you have the Qn. It is all located through the surface. Therefore, you have for this, the length element is what? For this, you have the length element, this delta A3. For this, you have the length element delta A, for example, A2. For this, you have the length element delta A1. This is delta A. It is a unit vector along the area vector, and this is the electric field intensity. So you see that look, what you will be doing this thing for every charge distribution. You see, look, for every shape, what you can say, look like this. For example, you just see, look, for the any surface, for the 1 you have the q1 into epsilon naught. For the 2 you have q2 by epsilon naught. For qn minus 1 you have qn minus 1 into epsilon naught. And for this you have the qn into, you have the qn into epsilon naught. If you add all the electric flux through the closed surface, then what will happen? The total electric flux will be q1 epsilon naught plus q2 into epsilon naught plus q3 into epsilon naught, qn minus 1 into epsilon naught, or then qn into epsilon naught. Or you just sum up, then what will happen? This is what a direct Gauss law I apply. A direct Gauss law. This is what? This is Gauss law direct application I wrote. So you see that what it will be, 1 over epsilon r times q1, q2, and up to qn minus 1 plus qn, and what it will be? Q, it will be 1 over epsilon naught, and what is this? The total charge enclosed by the surface, right? So what I will be writing, that this E psi will be equal to the total charge enclosed divided by epsilon naught. This represents the total charge, which is the Gauss law, and which shows that the Gauss law is applicable whether the surface is closed, or whether the surface is symmetric, or whether it is unsymmetric. But how to apply the Gauss law? That is, to apply the Gauss law, there must be what? There must be a closed surface, or what we can say, called the Gaussian surface. The Gaussian The Gaussian surface must be constructed. Must be what? Must be constructed first. You must the Gaussian surface. And second, charge distribution. What? Charge distribution. Charge distribution must be known, means the charge density, linear charge density if the charge is along a wire, surface charge density if the charges are distributed along a surface, volume charge density if it is distributed along a bulk on a body. So this is how the Gauss law is. So the Gauss law is one of the most important law which can solve complex situations, is very difficult to solve through the Coulomb's law. However, that is only applicable to symmetric charge distribution system. So thank you very much for being with me. Inshallah, in the next lecture, I will explain you some application of the Gauss law, the most important